All right, now in this quick little video, we're going to introduce Hund's rules. Hund's rules are used to figure out which term symbols that correspond to a given configuration are the most stable. All right, so what we saw previously is that for one configuration, we can actually have very many term symbols. They're all coming from orbitals that should have similar energies. And so the question then is which of these is going to be the most stable? If you're talking about the lowest energy configuration for an atom, this is equivalent to trying to figure out what's the ground state term symbol for an atom. But they can also apply to excited states, so they're actually quite useful. So we're just going to write these down. There are three rules, and they're all straightforward and easy to apply. So the first rule says that whichever state has the largest S, so largest value of spin, is the most stable. And it also says that the stability decreases with decreasing S. And what's really meant by most stable is it has the lowest energy, right? Okay, so as S increases, the energy decreases, or other way around. For lower values of S, we have higher energy. Okay. Rule number 2 then says if you have two states that have the same value of S, all right, so now this is basically the tiebreaker, then larger L means more stable. Okay, so the tiebreaker, if you have the same value of the spin quantum number, is then the angular momentum, and the larger the angular momentum eigenvalue, the more stable, or lower energy. So larger L means lower energy. And then we have one last quantum number that we need to use for a tiebreaker. And so if we have the same L and S, we need another tiebreaker, then this one gets a little bit more complicated. So we have two different cases here. So case A is if the subshell is less than half filled, then lower J is more stable. And then B, if the subshell is more than half filled, then larger J is more stable. Okay, so the rule kind of switches depending on the filling of the shell for this last case. That's what makes it slightly more complicated. All right, so let's do two quick examples. So first, let's talk about the term symbols for beryllium as an excited state. So if you think about the 1s2, 2s1, 3s1 configuration of beryllium, if you combine some of the things we've shown in previous sections, then you would see that the allowed term symbols for this would be triplet S or singlet S. Okay, and if we use rule number 1, then we can see immediately that the triplet S will be more stable. So the triplet S will be the lower energy configuration between these two. Okay. Let's do one more example. So the other example will be, let's look at the ground state of carbon, right? So the configuration of carbon will be 1s2, 2s2, and then 2p2. Okay, and what we showed previously again is that the allowed term symbols for this should be singlet S0, a triplet P0, a triplet P1, a triplet P2, and a singlet D2. All right, so these are all of the allowed term symbols that are commensurate with this configuration. And so now we can apply the first rule, and we can see that these three in the middle should be the most stable, right? These have the highest value of S. So the singlets will be lower in energy or higher in energy, less stable than the triplets. But then we need tiebreakers inside of here. So next we go to L, and they all have the same L value. So that doesn't help us. And then we need to go to one more level to get another tiebreaker. So now inside the same value of L and S, we look at whether the subshell is half filled. And this is the 2p2 subshell. So half filling would be P3. This is less than that. So we do the half filled rule. And then in the half filled rule, this tells you that a lower J is more stable. And so if we combine all of that, we would see that this one here, so triplet P0 should be the lowest energy configuration, the most stable configuration, and also the ground state. Then we can also rank order the rest, right? So this triplet P1 would be the next most stable. The triplet P2 would be the next most stable. Okay, and then we want to compare the last two. We first would look at the same rules will apply, right? So whichever has the largest spin, well, they both have the same spin, so that's not helpful. And then we keep going, we go to rule number 2. The larger L is then more stable, and so the D has a larger L than the S. And so we're going to say that the singlet D2 would be the next lowest, and then the highest energy, the highest energy configuration and term symbol would be this singlet S.